Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're going to do competition for the Titanic prediction, the classic Titanic prediction, but we're going to kind of step it up a notch and we're going to use the functional API so that we can digest and intake the name and the ticket, which are kind of just not random letters, but the name. Maybe that had something to do with uh, who survived on the Titanic, which is possible. Maybe some people were favorited because of their names, and then or their last names even. And then the tickets, like they could have been different places, maybe survived as well. So I always avoided this when I first started with data science, and I just thought it would be fun to kind of revisit a classic data set, but using a more advanced model such as the functional API in TensorFlow, we're able to have multiple inputs and multiple outputs, but we'll be using multiple inputs. Yeah. So get started by importing our libraries here. We have our classic standard data science libraries. We have our train test split, standard scalar, and then some stuff from scalar and small metrics, confusion matrix. This is to display, just get a very classic kind of confusion matrix look, and then accuracy scores we'll use. From TensorFlow, we're going to do TensorFlow, and then I have I never used to, but I've recently gotten really tired of writing the tf.k.layers. So I'm just going to import layers here and make it a little bit easier on ourselves today as we go through this. So just connecting. And then we have the data sets that we're using. I have from my in my GitHub reservoir to be able to just use this freely. You can go download it yourself if you wanted to, or save these as well. You can go to the link up here as well. Go right to the data set, or just go to the competition right here as well. And we'll use that, and I'll show you how to set up the predictions in the end. So what I'm going to do, I'm just going to save the past. Just notice here I'm using two data sets here. So the df comp is for the competition, and so I have to do the same things to this data set as well, just to be aware of. And we'll do this the same as we go along through this. So here we're going to need to save these IDs so that we can then put them into the final submission prediction after we have our predictions done. So right at the very end of the project. So just saving our IDs right here. Okay, looking at the head of the data set, and you kind of classic kind of Titanic Dataset. Okay, here, so just looking at, still we're going to treat this like a real data set. So here, just inspecting the univariate, the distributions. So figure, creating a fig size, and we do hist plot. And the next one we'll do, and we'll change the title as well. So we'll do this. And it just shows some, a couple colors just to kind of mix up here as well, just slightly different path. We're using more than one color because I want to change the hue by the target and really just see survived, not survived, how that really kind of played into all the rest of the features and stuff. And you can see here, I mean, it does in P class. It does seem to make a difference, truthfully, in lots of these films, like male and female, makes a huge difference. A lot more females survive than males. Would have sucked to be a man on the Titanic, and so I'm going to let you explore that yourself. Okay. So here, what we're going to do, we got to fill all this stuff just like we normally would, even though I know everyone's looking forward to the functional API. We want to really get through, make sure that we're trying to get good predictions. This is for a competition, so we've got to try as hard as we can. Okay. So here, and then what we'll do, we're going to fill NA of the median of the age, and again, doing this for the one data frame, and then for the, oops, I messed up filling correctly. And then fill in the NA for the competition data frame. So, okay. Going to look at dealing with outliers, so plots. And these are all were identified when I did the univariate analysis. And then hist, plot.hist, and then parentheses, and then we're going to look at clipping. So we're going to clip at 60. So clip, and then the next one is clip as well. So both of those. Okay, so going here, now we're going to have sibs. I'm not really sure what this one means. Well, it's an exponential distribution. The exponential distributions are tricky. They don't make a good prediction, so we're going to try and do and see if we can manicure this a little bit, massage this into something a little bit. So we're going to use the log system. Okay, so still not really perfect, but it's a little bit better than what we saw before. It's a little bit less accentuated with how exponential it is. And that's what we're trying to do. We're trying to massage it and to get it to be a little bit closer to where the average is going to represent the data set, because that will be a good sense of what our model decides on the final predictions. And so doing the same thing here, just mentioning now I'm going into the parch. So I did parch again here. I'm just noticing not the greatest, just some really kind of outliers right here. So what I'm going to do, I'm going to just do this sometimes just to kind of trim this. So just clip this a little bit, move this in a little bit. So I'm going to clip this in like this. So on. Okay, so we're getting like more like 3 values now, but we kind of moved everything together. A lot less of an extreme exponential distribution. We're a little bit faster, but just to kind of get through this, so that we can get to the designing the inputs and the architecture of the model. Okay, here, so doing log here as well. Oops, not log, and then taking the log of this. Lots of exponential distributions. I truly am my least favorite type of distribution is an exponential distribution. They're a little bit hard to deal with. Sometimes they work really well, and this is not perfect, but it's much closer to what we would hope from a log transformation, getting a more normal type distribution where the average is going to be sitting somewhere in the middle, and then will be much more representative of the data set versus kind of sitting way over here, really pulled in one direction, affected by the outliers. That will mean our model would, again, as well adapt to what works well for the outliers, and that just is not going to be good for our overall predictions. So what we're going to do is we're going to tokenize the name and then the ticket. We're going to do everything separately just to kind of make sure that we stay organized for one, and then making sure that the inputs and outputs get changed appropriately and accordingly. Okay, see, we're going to tf.keras.preprocessing text lowercase and then tokenizer capital T token, and then we're going to set our OOV out of vocabulary token to OOV, and then we're going to do, this is important here because we're going to do the char level. So what we're going to do is we're going to take the input, we're going to do convolution across it, so capture maybe 3 or 4 letters at a time. It's not full names, but sections of the name, and maybe those will be related to our predictions, and our model will be able to use those. And if you think 2 convolutions come together, you could eventually create full names or close to full names deeper into the network. Okay, so here what we're going to do, and then we're going to go fit. After we create our tokenizer, our on text speech on. Going all over the place here. Fit on text. Okay. Fit on text. And then I'm going to get the word index while I'm here as well. So word index. Then it will, in this case, I'm only going to use it to get the length of how much the vocabulary is in my data set, but it can be handy and used in many other ways. So I usually kind of just do it to save it just in case I need it later on. Okay, doing this again. So now we're going to do this for the ticket. So tf.preprocessing.text.token. And here we're going to do, it's the same thing as above, OOV underscore token for the out of vocabulary token, and then the char underscore level for the char level, so that we're getting each character. We don't really want the full words or the chunks of the words, the random series of characters. We could, maybe that would work good. Something for you to experiment with for sure. Only so many hours in the day to experiment with different architectures and different preprocessing techniques, because there is a lot. Okay, so fit on, not font, fit on text, and then we're going to go word index. Apologize for typing while I'm talking, just to get used to this workflow. Okay, so here we're going to do this, and we did that for now. We're going to do it for the token, the ticket. So TK is ticket, NA is name, and I just try to think of the really reduced variables that I'm using. Try to make them as obvious, but you're really just trying to get rid of vowels is kind of my trick, I guess you would say. To try to get rid of as many vowels as possible. Okay. Here what we're going to do is we're going to do an input here. We're going to do now this texts, plural, to sequences. Okay. So two plurals there. Plurals are always important in English, and they're really important in Python as well. Texts to sequences. Okay. So now getting the sequences for the name sections for both the training data set, I guess, or training data set, and the data set we're using in the competitions. Okay, doing the same again for the the ticket. Okay, so then we have texts, sequences. Okay, just make it easier and copy and paste that. Type that one enough. It's good to practice, but you know you don't need so much. Texts, sequences. And I'm just going to spell these correctly. That happens when you're not sure, because I couldn't really see what I spelled right there, even when I copied and pasted it. So go up to what you had before, copy and paste it, and then paste it over. Even if you can't see it, it's usually your spelling mistake. It's usually a good rule of thumb. So you get the number of our vocabulary. We're gonna get the length of the word index, which is why we got that up above. Okay, and then the length of the ticket, and then first the name, and then the ticket. Okay, and then here we're gonna get the max length of them. So we're gonna get the max of this comprehension. So we're gonna go length of sequence for sequence SEQ in input name. We're going to do the same thing here. You're going to go len for sequence in input ticket. Okay. And so the reason that we're doing this is to get the length of each one, and then what you're going to do is you're going to get the max of all the lengths, and still let you know the max length for then when we do the padding in the next step. We'll know how big we want to make our, and here you can see the name really long, 82, and the ticket only 18 and stuff. Okay. So here we're going to do our padding sequences. So we're going to go tf.keras, fill in the blanks, tf.keras dot utils dot pad underscore sequences. Okay, and then just to save a little bit of time, because it's exactly the same here. I honestly try to write everything out a lot, but I mean, I made this project I'm doing again, but it's good to practice if you want to practice build that muscle memory. I've done this many times, and this one thing I specifically know. They did change this actually though not too long ago. It used to be in a different sub library that you go into. So I was practicing a lot this new one just to get that muscle memory down, so I can remember where exactly I'm going. So I don't have to Google. It's okay to Google and find this thing, but it's nice if you don't have to. Let your fingers do it and memorize those things for you. Put your fingers to work. Okay. So going to pad sequences. Sequence. And we really got to spell these things correctly. Sequence. Yeah, spelling things correctly. Oh, English is so tricky sometimes. I always say that Python is my native language, but it's not true because it's in English still, and so it's tough. Okay, so one hot encoding now. We're going to do one hot encoding for our regular tabular data, so our features that we're going to use are classifying features. Are going to get dummies for category features here as well. So just make sure we're defining this list up above, get categories, and then so on. Yeah. So going through here, now we have our column names. So we're going to create these. You see all the column names in our training data set. We actually don't have the cabin data set in the competition one, so probably would give us a better predictions, but not able to use it. So I did not select them for the training of the first model because we won't be able to then do predictions. Okay, so features, making a list of our features, making a list of our target, then putting our features, selecting those out of the name, then selecting out the target, and I'm going to select, out the features from the competition data set as well. We don't need a target because we don't have a target. We're going to be predicting that, and then they'll tell us how good we did. But they won't tell us what the answers are. Okay, I'm sure you'll see a lot of 100% on those ones. I think those are probably people that somehow found the answers and stuff. Is probably not very likely. Okay, so here what we're going to do, if you think about this, we have two different inputs, we have three different inputs, and we're going to take one of those and split them up into, we go into an LSTM layer and a dense layer, but that's not when we get there. But we have to make sure that when we're doing this train test split, that we're also sampling our two other inputs, the name and the ticket that we get, right? So we need to now do a little bit more complicated train test split, but it's not so bad. We'll go slow though. So we're going to do our train test split. So we're going to put these, instead of into a NumPy array, we're going to put them into a data frame to be a little bit easier to select out these things. A little bit slower, like it's a very small data sets, so not a big deal there. Okay, so what we're going to do is we're going to do a train test split, right? So we're getting our features, train features test, output. Okay, so input features, and then our input name, input token. Okay, or sorry, not token, input ticket. Okay, so what we're going to do is we're going to do iLock, right? And we're going to go iLock of the index to get the train. So we're going to go to the train of this one. We're going to use that to get the train of the name from the input name, right? So we have all of them in the input N, NM input TK have all of our index or all of our name and ticket inputs. Okay. So then if we have that, we're going to select from that then all of our train indexes. And then we're going to do the opposite. We're going to go not in, do a list comprehension, not in list of these indexes. So I'm going to make an index of these ones. And then what I'm going to do, so this is a list of now what's in my train data. I'm going to say what is not in my original, the full data set. So of the index that is in my full data set, of the full input of the features name and features token, or sorry, ticket. I'm going to do those full ones. I'm going to say what's not in those ones. So which is in the test then. I'm going to select up there. So it's a little bit, it was a little bit tricky to think through the first time if you're not used to this comprehension, but it's good to think of just for integer, ind for value in list, I'm going to do this. And so I'm going to do true or false. I'm going to put it in here if it's not in the value. Then I'm also going to take the index for the features for the test indexes as well. Just found that out later on that I needed those, and so I came back up and did it. And you can see here we have the same number of tests in all of our tests. We have our same number in our train. We have the 755. Okay. And then we're going to standardize, just classic machine learning. We want to standardize our inputs, especially our numerical values. And we're going to do one hot encoding of everything with one hot encode to be less important, but since they're not, we're going to standardize everything to get it all on the same scale. Okay, so we're going to fit, transform, and again, we're just doing this on the features that we'll be using our classic kind of machine learning features. We're going to do this transform as well on our competition predictions as well. Don't forget about this competition. I got to spell. Not a good speller today. I got to spell transform. Okay. Good job. Getting onto the model. Dun, dun, dun. So this is not so bad. I'm not going to make this too difficult today. This is kind of having fun with a classic data set, and we're using it in a little bit more interesting way to see if we can improve upon what was there. So we're going to start with our functional here. We're going to start with our inputs, right? So we got what is going into our model, and then what is going out of our model. And I think that's why I do the names as input and output, because it just makes it easier to think through input and output instead of X and Y as you start building them up. So here what we're going to do, and what's really important is that we give our inputs and our outputs names. You should maybe give everything a name, but it's really important just highlighting here that we're going to give a name for each one of our inputs. Okay. We're going to then do, in our name section, we're going to put our name input into an embedding. Okay. We go vocab plus 1, the vocab that we got up above, plus 1. We're going to do embedding dimensions, mass 0. And here what we're going to do is we're connecting our input underscore name. Okay. Input name right here. So connecting this to this right here. And so this is how we connect them. Although it looks like we're multiplying this layer by this layer, we're not really multiplying. It's a quirk of Python. If you're a Pythonista, what it's doing is it's not doing the multiplication of these two functions. It's doing one function inside of the other. So it means one happens first, essentially. And this allows for the forward and backwards propagation and all the linear algebra and all those things. So it's just a way to define Python, and that we're connecting these. We're not really doing multiplication here. It's actually quite easy to use a function model. Okay, so here what we're doing is the cov. Now we're going to do a cov 1D. Okay. So cov D one layer right here. Then we're going to do an LSTM TM layer, and then what we want to do is a dropout layer. The dropout layers are super important. Then, so that was our block, our channel for the name. Then let's do our channel for the ticket. Okay, so we're going to do embedding again. We're going to then do a convolution of 1D. Then we're going to do LSTM. So we're doing convolution, LSTM, and then dropout. So kind of we're doing the same thing for these two sides. Then we're going to let the standard machine learning features, the tabular data, go into two different channels. So one's going to be a channel into dense layers and a channel into just the LSTM layer. So we have the same stuff right here. So you can see it's the length of our features. And here we're doing our max length and max length for the inputs of these two. I should explain that first, sorry. And then doing the dense right here. So we're doing our dense 1, and we're connecting. Oh, and I forgot to see some blue here. Don't forget to connect the embedding of our token, or sorry, ticket TK to the inputs of the TK right here. The TK right here. Just connecting those, and then we're going to do our densing, and we're going to connect this to inputs underscore dense. Okay. And then we're going to do another dense layer. Just have a little bit of complexity here, and then again, this is so we just connect this layer down to the next layer. This layer down. Well, we're going to connect all these down below, and then our LSTM layer just by itself right here. And we're going to make sure that we connect this to the input LSTM. Okay. And the big thing here is when we did the LSTM, we had to allow for the depth dimension to be able to do a recurrent layer on kind of tabular data. You have to do this comma 1, which took me a while to figure out the first time. Okay. And then just like we did for our target, we're going to do a name for our output, and we're just going to do a dense layer. Nothing's complicated. So dense, we're going to do a sigmoid activation, and we're just going to do one neuron. It's going to be a sigmoid, and we'll have trues and false, or we'll have ones and zeros for our target output, okay? Or probability of for 0 to 1. Okay. So here we're going to we define all of this now, so it's not so bad. And I do have some other stuff. I just left it. I'm just noticing I did have an LSTM in the head, kind of after I concat everything right here, concat a list of the outputs of my other 4 sections. And I put them on the list. I'm going to do it across the axis once. I'm doing it vertically, or sorry, horizontally. I apologize. So doing it horizontally. And I did have an LSTM layer here as well. I found it did not work. You can play around with this and stuff, but you just need to reshape the layer based on the size of the end block. Okay. So reshape it, and then LSTM drop out. I found it did not work very well, but it was having some fun and stuff. So it's really good. I just left it there to show that how really it's strictly not too hard. So we've defined the layers. We haven't defined our model, right? So we're going to do models dot capital M models. It's a really important model. Okay? And then the way that we define our inputs, we do inputs with a plural, and then outputs. Here we only have one output right here, and we're going to define it in a dictionary. So key is the name, and then this is the value. So this is the layer right here, and to the name. Okay. Layer name, layer name, layer name. Let's just make sure it didn't spell anything incorrectly. Is not defined. Oh, gotta run these hyperparameters first. Okay. One spelling mistake, not so bad. Okay. And that's a small one. Again there. So it's good, no errors right away, and we got that right. Okay, so we're just now defining the model. We're defining it in tf.characters.models.model, and then we're going to compile this model just like we would with binary cross entropy and then stochastic gradient descent. Find stochastic gradient descent was pretty good on spreadsheet type data, tabular data, and stuff like that, so it works well. So here, then what we're going to do is we're going to do model.summary. So we defined our model. We have our model now. Let's train it. Well, let's just take a look at it first. Get a summary of it. And you can see we have 158,000 parameters. So quite a big model for the Titanic data set. Hopefully this extra complexity yields a little bit of results. Okay. So then we're going to go model.utils dot plot underscore. So to give this the model that we just created, the functional model that we just created up above, you can see we have our two channels, taking in the name, the ticket and the name, and then just our dense input and our LSTM input over here. Okay. And then concatenating it, and then having our final target output. Okay, so then we're going to fit it. The way we're going to fit this, so remember we gave names, so we're going to do an index, or sorry, a dictionary for our x. X is equal to a dictionary. The name of the layer that we want to be sending our actual training data to, the name of the layer that we'll be sending our training data to, and so on and so on. So the names of the layer are the keys, and then our data is the value this time. So we pause 25, and then predict this. Okay. Let's go for 35 this time. So we have slightly different prediction. And here, actually, what I'm going to do, I'm going to do my validation data is to try use as much data as we can in our predictions. So we did a train test split up above, and we're going to use that to help do our threshold tuning, just in a very simple loop that we have down below. And then what we're going to do here is we're going to do another validation. So try not to use too much data. This is sort of a very high accuracy on our training data, but that is likely just the very few samples that we have. Hopefully, maybe about 68%, 86% on our but yes, no. Yeah. So let's start working. So these are some of my notes that I keep. This is a good way to kind of keep my notes. I just copy and paste the hyperparameters up above, and I'll just say, I'll put a star next to what I'm experimenting with this time and kind of going through it. You can do your model into loops and stuff like that, but sometimes with the functional, it's just a little bit too big to be putting this into a loop and experimenting through. So hopefully you got lots of practice experimenting with the sequential model, so you have a good intuition of how you should be experimenting from there. We're going to do our plotting history right here. Down below, we're going to do our predictions for our target. So if we predict on our test data, and then we're going to do lim space. And we're going to go from 0 to 1. We're going to hover number. So we're basically going to get every number between 0 and 1. So we can do our threshold, the sigmoid, where we're going to set, it's this class or that class. And we're going to find so we iterate through this. We find our best actor is 79, and our best threshold was 78. Okay, so this helps us. Then we're going to do the final thing where we do our confusion matrix, and then we do our test submissions below. So let's do confusion underscore matrix. And then this one's using the sklearn display confusion, and they're all capitalized matrix. Okay. Display confusion matrix. And then to show how we do the fun predictions. So just noticing here, what I'm doing is I'm setting my best threshold that was found on the first testing set. And I'm going to times this by 1, because now you're going to get trues and falses, and the submission specifically wants to see trues and falses here. We want to do it times by 1 so that we get zeros. We get 1s and zeros right here. So you can see that. So you get that. And then we're going to put this into a data frame. I'm noticing here I'm actually doing the multiplication times 1, so you get 1s and zeros. Then I'm going to put the indexes that we have way up at the top. I'm going to then put those two things into, I'm going to make sure I switch the ordering just because I wanted this in certain order for my predictions. So make the predictions, and let's see what we're going to kind of far along the trade. Okay, this looks like we're finishing our predictions. Looks like we got 86 on our predictions. Let's see what our training history looks like. It looks like we flattened light. We probably didn't need to train it for 35. We're not necessary to train so much. So looking at our predictions, and then here we're going to do is our loop that we did. So we predict, and then we put in line space. So we're iterating through every lin space. It's not line space, it's lin space. That's what it's put on the brand. And then we're iterating through this, and you can see here we got a slightly different. Best accuracy was 81, and we're going through 62. Didn't change anything this time. Your model is going to start at a random place in the gradient. It's going to slide down. So where it started is going to have it, it's going to be different. It's going to be a slightly different prediction. So every time you run this, by default, you would get slightly different predictions. And so running this, we'll see we get our confusion matrix, and pretty good predictions. Let's see. Hopefully, it was the best one I've seen. So let's see what we do. So let's predict. Let's get our multiplying 1 by 1 just to show what this looks like. And then we'll put this into a data frame. We're going to call it the survive column. We're then going to put our indexes back. We're then going to create, switch these two routes so they're in the right ordering for our competition submissions. Saving this to a CSV, and you can see what our predictions of passenger and survive. So let's see, let's take this. I'm going to do predictions right here in the little down mode using Colab. And I'm going to go all the way back up to my top. I'm going to see go up to my competitions right here. The link that I have. Submit predictions, browse files, and then we'll go downloads and just go to one that I just did 2 seconds ago. I was experimenting, so this is not my first time. But we'll see if I did better than my other ones. So 77. So this is the one that I just did right now. So 70. So not as good as my other ones. And that's the thing. It said my validation said I got 86. That's one of the things I'd be a little bit humble about, but pretty good. Truthfully, I'm in. If we go to leaderboard, okay, and you can see here the way that you can. And my score is my best score here is I got 78. So a little bit of improvement over some of my other scores, but I think I've been able to do quite a bit better here as well. Not above the 2000, so that's one of those things. But you can see here, there's lots of these people. I'm pretty sure this is not a real submission to get 100%. I don't believe that. And you can see, so there's a lot of maybe cheaters going on here, but I think 82 is, from what I've heard, is about the maximum that I've seen justifiably done. And so thank you very much for joining me today on this Titanic Kaggle prediction using the functional model. Thank you so much.